Let's see. Did any of you catch the joke that Francois was just making about Chris signing a laptop? Probably not, right? So, what?
It's not a joke.
Well, it's not a joke, but let me just tell the story. We were at WWDC this, a couple months ago, and someone actually asked Chris to sign their laptop, autograph it. And all of us were kidding Chris about that. But I've been working at Apple for quite some time. I won't say how many years. I've hung out with all the big guys, and they've never been asked to sign a laptop, but Chris. So I was just blown away. Anyway, Chris has really made it in the Apple community. So I'm Steve Naroff. That's my coordinates. It's naroff@apple.com. So Clang. How many folks know what Clang is? I would imagine mostly everyone. Okay, great. So it's actually not much of a C++ front end yet. It's starting to be a C++ front end, but it's very much a C and Objective-C front end today. Certainly there are bugs, there are things that we're still working on, but it's quite capable, and I'll be talking about that throughout the talk. We want it to be a drop-in replacement for GCC. We understand that not only does most of Apple's code, or all of Apple's code, compile with GCC, most of the world's C code compiles with GCC. Tremendous amount of it. So we can't deviate from GCC. We don't want to make Clang adoption difficult for people. We want it to be very straightforward. So compatibility with GCC and the standards are very critical to us, and that takes a lot of work, obviously. It's also part of the open source LLVM project, same design point. I'll be talking more about that later, but we're really excited to have Apple bless the open source. Last year, when I was here speaking, it was not open sourced yet, and now it is. And we have many great contributors across the globe, so it's very exciting. So let's look at a timeline. In June of 2006, Chris gave birth to Clang. And he worked a lot on the core infrastructure, lexical analysis, pre-processing. Writing a C preprocessor is an extremely challenging thing, especially writing one that's efficient as the one Chris wrote. And when I saw this work, I wanted to become a part of it, and I joined Chris in October of 2006. And I worked a lot on the C parsing, the semantic analysis, the abstract syntax trees. And since then, I've worked on a lot of other stuff, and we can go into that later. I spoke about this last year. There were about 40 folks here, and we introduced Clang. And I focused on a different set of things that I'm going to focus on today. And in July, Apple approved the open source. And so from June of 2006 to July 2007, a lot of interesting work was done, but it was still very much in an early stage. So last year, when I was giving examples, Clang could compile some of our headers, and we gave some benchmarks, but it wasn't compiling large source code bases. At the moment, it's compiling very large source code bases. July 2007, again, Apple approved that. Now, in June of 2008, we introduced it at our Worldwide Developer Conference. Hey, Apple's Worldwide Developer Conference is a very big event, and typically we only talk about shipping products. Getting Apple to approve us to talk about something that is in development, like Clang is extremely unusual. But Apple gave us the go-ahead since it's in the open source, and there's a lot of interesting work, and we're very committed to it, to talk about it. And I was actually blown away at how many people were enthusiastic about this. I really was. I expected more pushback, like, oh, we don't want to switch compilers. Why would we switch compilers? You know, GCC is good enough. Please, leave us alone. None of that. Almost none of that. Tremendous excitement around Clang and LLVM. So from July to June, these folks were the key contributors. Ted Kremenek has done heroic work on the static analyzer that he'll talk about later on. He's also contributed a tremendous amount to the core infrastructure, ASTs. Fariborz Jahanian has worked on Objective-C along with me, done some incredible work. Devang's worked on the back end. Anders Carlson, who's here, has made many improvements. Eli Friedman's worked on the back end The back end is roughly 70 to 80% done. Still some work there. Argyris is someone who's working on the C++ front end for us. He's not able to be here. He works out of Greece, I believe, and that's sort of a far commute for him, so he didn't come to the conference. David Chisnell has done the back end for the Objective-C GNU runtime, and Nate Begman has made various improvements. And there are other people. These are just the key contributors over the past year. And we hope in 2009 to have a native compiler for C and Objective-C that's fully functional. So that's the timeline. A lot of progress in 2 years. Really amazing. And when we first started this, I think some people thought we were crazy to try and be GCC compatible and somehow be a replacement for GCC, because GCC has hundreds of man years of development. But we think with good architecture, the right people, we could actually pull this off, and it's starting to look real. So our key motivations. Fast compilation. This is something that we believe, unless you design it in from the beginning, it'll never be quite as great as you want it to be. So from the beginning, speed has been a goal. Another point on speed. We want the compiler that's working at the command line, so to speak. We call it sometimes a batch compiler. We want the batch compiler to be fast, but we also want to architect our objects and our frameworks so that we can make it fast when you're in an IDE, let's say, where you have more opportunities to cache things. And I'll talk more about that later. Expressive error diagnostics, I talked a lot about this last year. I'm not going to talk at all about it today because Ted's actually going to do a talk on static analysis and bug finding, which will cover this aspect. And what I am going to talk a lot about today is the foundation for new programming tools, right? So we want to spur innovation. In the C compiler realm, most of these compilers were built in, let's say, the 80s and 90s, and the primary goal there was, how do we generate really good code? That's what the focus was. Writing static analysis tools, writing refactoring tools. There's a lot of other things that people want to do with front ends that these parsers were not interested in at the time, really, and in fact, retrofitting is really hard. So we want to make sure our architecture accommodates a lot of the features that I have listed there. I want to talk a little bit about what I mean by progressive. In some compiler communities, even using object-oriented programming techniques is considered a radical idea, right? And at Apple, we've benefited significantly from object-oriented programming. We believe those benefits actually are as important for compilers as they are for GUI programming kits or other kits, animation, whatever. And so we feel strongly that an object-oriented architecture is critical. It just so happens we're using C++ because it's a wonderful language for writing a compiler, but we're not even religious about C++. We're more religious about the architecture and what we're trying to do. The other thing about progressive is the LLVM community is an extremely kind and gentle and mentoring community. I think this comes from the top with Chris. I used to work in the GCC community, and it was different. And when I was 26 years old, I could deal with the people there. I'm older now and don't want to deal with that. In any event. And certainly the modular LLVM-inspired architecture is very important to us. So again, we're going to talk about static analysis today. Refactoring is another feature we work on across all this stuff. Incremental compilation is probably the most challenging, but you can interpret incremental compilation in many different ways, right? Certainly, when you're a batch compiler and you're forced to read the files off the disk, it's definitely not incremental. But as soon as you start caching things in an IDE or any other program, it starts becoming incremental, right? So there's many interesting things we could do there. I just have one slide here as a check. I'm not going to talk much about performance. Last year I said we were 2.5 times faster than GCC for batch compilation. At the time, it was just running it over our big header file. Here, we're compiling Postgres SQL, which is a fairly large code base, and GCC 4.2 compiles it in 49 seconds. We compile it in 21 seconds, and it's 2.3 times faster. So it's a little bit slower than what I said last year, but since we don't have A/B compares, it's really hard to do precise analysis there. The point is, we're about as fast as we said we were last year, and that's good, because the compiler is actually correct, more correct than it was last year. I have more detail slides on this type, but I didn't bring them today. But the breakdown is roughly, and this may surprise some of you, 65% of the time we spend in pre-processing and lexical analysis, 25% of the time we spend doing semantic analysis and AST building, and only 10% parsing. Okay? So while the parsing framework I'm going to talk about in a little while is layered and reusable and really nice, it's not our performance problem. Okay? Our big performance issue is pre-processing. And interestingly, when you're in an IDE, there's tons of stuff you can cache. So the good news is that 65% number can be improved on significantly. So let's look at the Clang architecture and libraries as a review. So Basic. Basic is a library that deals with source. We have a source manager object, file manager, it deals with diagnostics. Basically a lot of nice objects for dealing with language independent concepts. Lex is the first library that deals with language specific things, lexing tokens in C and Objective-C. Now Lex is conceptually simple, right? It takes characters, turns them into tokens. But what's not simple about the Lex library is it contains the preprocessor. The preprocessor and Lex do this very tight dance that for efficiency. So, but we have one library that has the lexical analyzer and preprocessor. The parser there is a recursive descent hand-built parser that Chris and I wrote, and it is it works well. I mean, I'll talk more about that later. Some people think doing or using compilers is the way you need to go, but we think this hand-built parser is fairly easy to maintain and nicely done. The abstract syntax tree are a bunch of C++ objects that model the source code. Even though it's called an abstract syntax tree, it's fairly concrete. The objects are not very abstract at all. The one thing that they don't contain, that traditional compilers contain, are details on the code generation. So these ASTs purely reflect the source code. And they're designed to be small, and they're designed to be written to disk and read from disk, right, for eventually doing precompile headers and other fancy things. SEMA is an actions module. I'll tell you what that is in a minute. And what that does is do semantic analysis on C and Objective-C, and it builds the trees. So that's the core library. On the right side, we have analysis, which Ted's going to talk about, the static analysis application of Clang, which is still written as a library. So our approach is not only to build our infrastructure or our core using libraries, but to also build Clang applications using libraries so folks can layer their applications on top of that. The rewriter is an interesting library for doing refactoring. It will basically take code fragments and replace code fragments and insert code fragments. It's a very interesting library. And LLVM gen. LLVM gen takes ASTs and produces LLVM bytecodes. At last year's meeting, that was a fix me, and now it's pretty far along. So, and down below, just to emphasize, these libraries can be used by a command line compiler or by an IDE. Today, I'm only going to talk about what's on the left side, and in particular, just a few of those libraries. So let's start. We have Clang components at the lowest level. We have a lexer, a preprocessor, and a parser. And very simple stuff. You call in. The parser asks the preprocessor for a token, and the preprocessor in turn will ask the lexer for a token. Very straightforward. We have these Clang parser actions, which are an abstract interface that corresponds to roughly the language elements in the C and Objective-C grammar. And that's abstract. So there's a whole slew of act-on delegate methods. The most complex set of delegate methods are for declarations, because C declarations are complex to parse and analyze, and they include types, and C types are complex to parse and analyze. So that makes these actions, they're as straightforward as they can be, we believe, but ultimately you really have to understand the C language to implement these actions. The expressions and statements are very straightforward. They're very regular. So I'm sure even if you don't have a compiler background, writing those actions is very straightforward. But for most of you, you'll be using the CIMA action module. So it comes with an action module that most people are going to be using. And as I said, it does a semantic analysis and type checking, and if it's not well formed, if it is well formed, an abstract syntax tree pops out the other end. If there are problems, then you don't get an abstract syntax tree. So the design point is when you have an AST, you know that it's well formed, right? The other tools in the chain do not have to be paranoid about the state of the AST, okay? There's one minor exception. When we're parsing declarations, declarations are so coarse-grained that there is actually a bit in the declaration to say whether there was an error in it. But in general, you don't have to worry about that. Yeah?
Do you have to build up the data structure in your CIMA actions? Isn't it typical to build an AST and then do analysis on that? Correcting or...
That's where we're different. No, we do the analysis, and then what pops out is a less abstract syntax tree. Right. Oh, okay. Take the questions at the end. Okay.
Well, repeat the question.
Oh, repeat the question.
Well, actually, you repeat the question.
Well, can we do it later? Let's do it later.
Okay.
So here's an example of one of the specific delegate hooks. I'm starting simple. So act on numeric constant. If you have a C numeric constant, the token will be passed in. CIMA will do the checking, and then what pops out is an integer literal or a floating literal. So the semantic analysis is not done in the lexer to determine whether it's an integer or float. It's done in CIMA. And this is because in C, you could have a constant with L's and U's and dots and all kinds of stuff. And that analysis is done by the semantic analyzer. The constant ultimately has to have a type, and that type is determined by CIMA, right? The next action I'll show here is a little bit more complicated. If you have an identifier, right? You have a variable, X. It's passed in a scope object, a location, the actual identifier, and then this funny argument at the end, which is because we're dealing with C, has trailing paren. So in that case, the semantic analyzer, if it's looking at an identifier and that identifier is, let's say, a function call but doesn't have a prototype, it needs to know whether there's a paren trailing it. And here we have a decal ref expert, which is the common object that pops out, but if you have an instance variable reference or a C++ member reference, that's what pops out. And lastly, we have an expression here. Let's say you want to act on a call, a function call. These expert type defs are just there for documentation. The CIMA actions take untyped objects, right? Because we want the actions interface is generic enough that we want you to be able to supply your own objects. Talk about that in a minute. But they're there for documentation. So here you have the function that's called, which is an expression, the location of the left paren, the arguments, the number of arguments, and the locations of the commas, and then the locations of the right paren. Okay? That's how it works. So now let's, just to emphasize the design point, is we have this thing called Clang-parse-no-op. And what this does is just implement 6 act-on methods to do type recognition. Type defs, classes, and Objective-C that you need to parse. And this doesn't produce any diagnostics, and it doesn't produce any objects, but it does parse the entire program. This allows us to do timing analysis. Okay? It also promotes this clear separation between the parser and the semantic analyzer. So for example, a lot of our tools are going to be based on action modules. Okay? Let's say one day there was some compiler that we absolutely loved, and we were sick and tired of maintaining the hand-built recursive descent parser. It turns out that as long as that new parser implements the set of actions, we can do a brain transplant and disrupt none of the code that sits on top of it, right? So because of this clear separation, it allows the parser to be reused and replaced really easily. And again, because we spend only 10% of time in parsing, this separation gives us a lot of bang for the buck, because it's really not a performance problem. AST requirements, we want to support multiple diverse clients. You know, modeling a program for diverse clients is actually a tricky thing. It requires you develop those clients hand in glove with the data structures. So we are developing many different applications to basically validate what we've done with the ASTs. So for example, one of the modules I wrote over the past year was a fancy rewriter that refactors code from Objective-C to C code. Okay? And to refactor that means you have to get the line numbers correct. Okay? And when I was doing this, just as sort of a fun project, it showed bugs in the source location stuff. Some objects didn't have enough source location. Sometimes the source locations weren't correct. So again, as we develop these libraries, we need to have little projects and exercises that validate what it is we're doing. We want them to be high performance. It turns out that there's only a small number of objects that you really need to care about performance on, identifiers and types in particular. So we unique them, and qual type is a smart pointer class for storing, you know, the type qualifiers and selectors. So these guys, we don't have to go into detail, but if you look at them, they've been highly optimized, yet they still have a nice interface. Okay.
Steve, you have about 10 minutes left.
10 minutes? Okay. Thanks, Ted. The integer literal class, here's just to show you a simple class. It leverages the arbitrary precision integer in LLVM. There's a constructor, there's getters, very straightforward. It does an assert in the constructor to make sure the type is correct. And here are iterators, serialization, and dynamic type support. So the serialization are the hooks that write the object to disk and read it. Iterators should be obvious. I'll give you an example in a minute. And the dynamic type support, these are hooks that are infrastructure that you implement. You rarely call this. Here's Clang AST dump, a very simple function. And here's what you get out to show you the representation of the AST. Shows you the line column information, the types, and the structure. Here's a slightly different example with a float. Notice it inserted some implicit casts. So even though the ASTs reflect the source code, sometimes the semantic analyzer will adorn the AST with information that reflects C. So for instance, C does default promotions when you're mixing integers and floats. So this reflects the C language, even though it's not directly in the source code. Here's another switch for viewing the ASTs using GraphViz. It doesn't contain as much information, but certainly someone could go in there and add as much information as they want if they determine that this is a useful tool. For most of our debugging, the previous dump is much more useful for us. So tying some of this together, here's, let's say you were using AST dump and you were frustrated with the volume of information that was coming out and you wanted to write a custom little function to just dump all function calls. Well, that's what this code does. There's an AST consumer hook that gets called. This call dumper iterates through all of the statements, and here, using the dynamic cast mechanism, checks if it's a call expr. If it's a call expr, it dumps it, right? Very clean, very easy, and that's the spirit of the ASTs. So how many minutes do I have left now? 5?
Yeah, about 5.
Okay. Extending Clang. So you can traverse the ASTs, as I just showed you. You can traverse the CFGs, which is a control flow graph that Ted will talk more about. You could use built-in data flow analysis, which is also part of the analysis library. And lastly, if you're bold, you could implement a subclass of minimal action, right? Let's say you were writing a source code browser and you just wanted to pull out the class names or the method names, and you don't care if the code is incorrect. That is, you don't care that semantic analysis would choke on it. Then you would write a subclass of this, and it would be a fuzzy parser, right? Not syntactically fuzzy, but semantically fuzzy. If you wanted to write a syntactically fuzzy parser, you could use our preprocessor token stream, right? So there are many different options you have for reusing Clang. And if you want to add a new language feature, well, you have to hack the usual stuff, right? Hopefully, if you're designing a language feature, you understand the language. So if you understand the language, hacking Alexa, parser schema, all this stuff is just part of the job, right? So, but we think a lot of people are going to be writing tools without adding language features, right? So it's a different client. Status, C and Objective-C parsing mostly complete. We have some missing details with variable length arrays, some GNU extensions. We can parse huge source spaces, and we're very excited about it, and a lot of people have helped in the community to make that so. I don't need to repeat that since I'm running on time. And C++ parsing, Argyris is doing some really great work to start enabling C++. And there's a link you can go to. So related projects, we don't have any debugger support. So everything you write in Clang needs to be perfect. You cannot debug it. And because of static analysis, maybe it will be perfect, right? No. We're going to need a replacement for libgcc. We're going to need headers. And Anton is doing some work that might be interesting for the compiler driver. So there's lots to do here, and we'd love to get some help from folks in the community. I'm done.
So please repeat the question.
I will repeat the question. I will take a drink first. Okay. Yes?
Does the lecture preserve comments or cut it?
Does the lecture preserve comments? Yes, I believe there's a switch to preserve comments. We don't, I think it's off by default, but there is a switch to preserve them.
So one of the big problems for static analysis tools and refactoring tools is the preprocessor and the fact that you might actually want to analyze multiple build configurations of the code. Is there any support in Clang's preprocessor support to be able to, say, parse multiple conditions at the same time?
So I'll paraphrase. That's a tough question to repeat. Is there any fancy built-in support for when doing refactoring or rewriting to deal with multiple branches in the preprocessor? You know, if you have an if-def or an if clause. The answer is no. Nothing fancy built in. But like a lot of our objects could be extended if there are great solutions to that problem. I don't feel there are great solutions, but you know, I think Rob, you're great, and you can contribute and help us solve that problem. Okay, yes.
So one of the early slides talked about compatibility with GCC. So will it stay compatible with the future releases? GCC?
Okay, the question is, there's compatibility with GCC as it exists today, roughly at 4.2 in our world, and will it remain compatible in the future? I can't predict the future, right? The intention is to be compatible with the mainstream of GCC. So for now, we're just worrying with the current mainstream. In terms of what's going to happen in the future, I can't predict that. Our intention is that if the world continues to use GCC and a lot of that world wants to use our product, we will do that. But that's such a dynamic question, I can't really answer it fully.
A lot of it depends on patches. Contributors.
Contributors, patches, right. I mean, if more of the GCC community were to start contributing to Clang and bring those things over, then that would be done for us. Yes?
Yeah. So I noticed you have a pretty solid date, well, a year for full C and Objective-C C support. What about C++?
So the question is, well, first a comment that it looks like we have a good plan for C and Objective-C. What is the plan for C++? I didn't say much about that. C++ is a really tough language, right? And we have some very talented people working on it. I can't, from where I sit, project. It would be disingenuous if I said, oh, 2010, right? It's easy for me to say, oh, if this is in 2009, then that's in 2010. I have no idea. Conservatively speaking, we're probably 2 years away from any credible C++ support in Clang. Chris, do you concur with that?
Yeah, 2 or 3 years.
2 or 3 years.
So no self-hosting for a while.
No self-hosting for a while.
It's a very important problem to us, but this takes time. It goes faster without.
Yeah, we can get Bjorn and Doug Greger. And
Doug is spending all his time hacking on GCC these days. At least you didn't say it's an important future direction.
And also, there's the next iteration of C++, right? Let's not forget that. That throws a wrench into the works, too. So.
That's what Doug is hacking on C++.
Exactly.
Or on GCC.
Yeah, Doug is a very talented guy. Yeah.
And you were talking about library stuff. You have a very talented guy working for you in Howard.
Yes, that's right.
If you're going to need a new C++ runtime library,
You're absolutely right. We're well positioned there. That's true. Great. Well, thank you.